Right. Thank you for coming, those of you who did. We're going to talk about profilers and why they're not good and when they are good. My name is Nitsan, and I work as a performance consultant, so I get to look at profilers quite a lot and get to deal with people who look at profilers and get confused. So this is why people often turn to a profiler, because this is a survey that was done by Zero Turnaround, and they looked at why do people think their code is slow. That doesn't mean that people are right, but that's what they think. And 51.5% of people think that their applications are slow because their code is slow. Now, how do you know which part of your code is slow? You can just read the code and have a theory, or you can use a profiler, which is what you should do. So, I don't know how many of you ever profile? Excellent. People who don't profile don't bother showing up, which is good. We don't need them anyway, right? Most developers don't profile because profiling is not an activity that is covered in most computer science degrees, or maybe because people don't get to performance until after they've released, and then maybe it's somebody else's problem. When they do profile, this is what the same survey told us about what kind of tools do they use. And most people use JVisualVM or derivatives thereof. Who uses JVisualVM? Okay, I hope you'll stop. And who uses Java Mission Control? Okay, 2 people. Who uses perf? Okay, well done you. Okay, right. So all of these profilers have, some of them have instrumenting modes, some of them have sampling modes. We're going to talk about sampling profilers, and sampling profilers generally work by sampling a program on an interval. So every once in a while we take a sample, we take a stack trace of what's happening. We hope that the distribution of the samples will reflect the time spent in the application, and then we have some assumptions. We assume that the samples are random. If they're not random, this whole distribution thing is not going to work out. If the samples are always on the same line, then obviously we're not going to see the rest of the lines. And we hope that sample distribution approximates the time spent distribution. That is not always true, in particular if the interval isn't a time interval. And for some profilers, that's not the case. So more on that later. And the picture looks something like this. We have the time axis at the bottom, and we have methods calling into other methods, and it's raining samples from above. And we collect all of these samples. And what can happen is, like we see at the top, that there's a method. We don't know what it is because we've never seen a sample that includes this method. If we collect enough samples, then we should get a pretty accurate picture of what's going on. If we collect too few samples, then it's quite likely that we're missing something, right? So we're going to start with a very humble ambition of finding a line of code in one method that we're profiling, and we're going to look for the slow lines of code, so the lines of code where most of the time is spent. We're going to want to optimize them, then we're going to win. That's the theory, right? So we should be able to find slow lines of code. So we have our super important method. Over time, we rain samples. And then somewhere in super important method, we will have samples and find out which line is the expensive line. Now, this is not actually important code. This is just some code I typed out, so I would have a sample. But the idea here is important. If you have a tool that is a measurement tool, you can trust it blindly, which I don't recommend, but you could. Or you can try and calibrate the tool. You can try and see, this is a bit of code that I understand, that I know what it does, and I know how the performance of it should scale. And I'm going to profile that, and I should see results that reflect my understanding. And in this case, the performance of this code should be a driven by the size of the buffer. There's two loops here. One of them does more work than the other. I would expect the profile to reflect that. I would expect the slow lines of code, the expensive lines of code, to be within the loops. Anything else would be weird. All right, so we started by discovering, not surprisingly, that most of you use JVisualVM. JVisualVM, like most of the profilers on that slide, suffers from Safepoint bias. Who knows what a Safepoint is? It's always the same people. Right, Safepoints are a product of how JVMs work. Who knows what a stop the world pause is? Who's heard of garbage collection? Right, excellent, garbage collection. It's part of the Java that we love and know. Garbage collections induce pauses. This is why we don't like garbage collections. And garbage collections induce pauses that are stop the world pauses. That means they stop all of your threads. They don't stop all the threads, because if they stop the GC threads, then nothing would happen, right? So they stop all of the Java threads, and then the GC work can happen. That's an example of a Safepoint operation. So Java profilers that suffer from Safepoint bias only sample your code at Safepoint pause, which is where your Java threads can stop. They stop all of your threads, and then they look at where they are. So each sample is a Safepoint operation. Each sample includes all the threads, and it stops all the threads. So ironically, the profiler can only see your threads when they're not doing anything. They're just stopped. Okay? And it tends to work something like this. The green threads are Java threads. We will ask all of them to stop. Some of them will stop early. Some of them will stop later. Okay? Then we will do our Safepoint operation. In this case, collect the profile, collect the sample. And then we will release, and they'll just get on the way. The red thread here, the red arrow, is a native thread. Native threads don't need to stop. It's not that they don't need to stop as much as we have no way of stopping them. Because the way the JVM stops threads is by asking them to stop. It doesn't interrupt them, it raises a flag, and those threads every once in a while pull that flag, that's the Safepoint pull, and they stop voluntarily. So we don't have Safepoint pulls everywhere. We have Safepoint pulls typically in one of two places. We have them on method exit. Depends on the JVM implementation. Sometimes it's the exit, sometimes it's the entry to a method. And we have them in some loops. We don't have them in all the loops, only in loops that the JVM considers very long-running loops. So we will put a Safepoint pull in there. So if we take another look at this method, we have 3 candidates here for where Safepoints might happen. Okay? Now, that should be where all the blame goes when we profile this bit of code. Who thinks it's going to be on line number 5? Who thinks it's going to be on line number 10? Line number 13? The rest of you are non-committal, which is a good thing, because if anybody asks you a question about performance, always say it depends. You're probably always right. So with JVisualVM, 100% of the blame goes to the first loop. It doesn't go to the last line of the loop, it goes to the first line of the loop, which is pretty arbitrary. Why that line of code is so expensive? Is increment the counter really expensive? Is the condition really expensive? No. It's just that this loop happens to have a Safepoint pull in it, and the JVM happens to stick the blame not on the back edge of the loop, which is where we say, if we're not done, go back to the beginning, but on the beginning of the loop. It's completely arbitrary, okay? Now, if we hoist the divisor out of this loop, because the divisor is a volatile field, which is why the loop, again, it's completely arbitrary, but that's why that loop had a Safepoint pull at all. If we hoist that out, we're back to the same position. Where is the profile going to be? And now we have 2 different results for 2 different JVMs. Zing blames 100% on the first line, and Oracle blames nothing. This whole method costs nothing according to the new profile. So Zing blames 100% because Zing does Safepoint poll at the beginning of the method, not the end. Oracle blames nothing because, hey, if we're going to blame the end of the method and we're just about to return, why blame the method at all? Let's blame the next line to happen, okay? So if you have profiles where you look at it and you say, there's no way this is happening, how come nothing gets, this is why. You're just looking at completely bogus data, which leads us to this conclusion. Safepoint bias profiles are potentially very, very, very misleading. Now, that's not to say that the tool is completely useless. It's just useless in most cases. It's useful for one thing, which is looking at blocked code. So if your code is already blocked, the observation of where it's blocked is probably accurate. So if you have an application that's not actually using a lot of CPU, a lot of threads are blocked, a Safepoint biased profiler can still give you good information on that. They tend to do the right thing. Okay? They sample on a timer, so samples happen reliably every fraction of time. As we move on to other profilers, that's not going to happen anymore. Okay, so mission control. It's the next thing. It's the new profiler in the JVM box. Is it any good? The answer is a little bit. So better profilers, and mission control is a better profiler than JVisual VM, don't suffer from Safepoint bias. Okay? They sample at a signal, and that signal, importantly, is not driven by a timer. It's driven by the number of cycles your application spins. Okay, we'll get to what that means for you in a second. Each sample will include one thread, not all the threads in every sample, just one thread. We stop that thread, and we collect a sample we walk the stack. So this is a bunch of profilers that use the same methodology, Java Mission Control, Honest Profiler, and Async Profiler. They still provide wildly different profiles. But there's a common feature here. If we do nothing and just start using them, they will give us this profile. They will blame 100% on the first line of the first loop. That is patently false. Like I said, there's two loops here. They both scale with the size of the buffer. The second loop should get some of the blame. Also, that first line, why that first line? Why not any other line? And the reason for that is that JVM is very clever. And the JVM knows that all of you are using JVisual VM. And it knows that nearly none of you are using Java Mission Control. So why generate debug information that nobody's going to use, right? So it doesn't. Better profilers need better debug information. So by default, we don't have that. You need to enable this flag. So if you're using Java Mission Control and you're not turning this on, please turn it on. Even if you're not going to profile, just add it to your list of favorite flags that you're always turning on. So in case you ever need to profile your application, you will get something meaningful out of it. Okay? Should be the default, isn't the default. It's probably going to add a couple of megabytes to your memory usage, but in this day and age, you have more memory than you know what to do with anyway, right? So just turn it on. And when we turn it on, we get a much more reliable profile, okay? Some of the blame, most of the blame goes to the first loop, some of the blame goes to the second loop. Life is great, okay? We get a view into what's happening here, and this is definitely an improvement. Before you go and use mission control everywhere, there are some problems in there. In particular, code profiling with JFR, with Java Mission Control, is a little bit broken. When it fails to collect a sample, it just doesn't tell you about it. And ironically, it fails to collect a sample in places where the JVM has made special effort to make things go faster. So it goes from, it wasn't very fast, and then we implemented an improvement, and now you can't see it. Okay, so you have discussions, for instance, on the Cassandra mailing lists. there was a long drawn-out discussion about using their own hand-rolled CRC algorithm or using an intrinsic. They switched to using CRC32, which is an intrinsic, which means it's a special method that the JVM pre-generated for them. And then they can't see that cost at all now. It doesn't mean that it doesn't cost anything. It just means you're invisible to it, so you'll stop complaining, so it'll never become faster ever again, right? Also, some native code, for whatever reason, Java mission control fails to see. So if your application has a lot of network kind of facing code, if you're using Netty, a lot of the cycles spent in there are just going to disappear. To be clear, I don't mind that it fails to sample. I think it's absolutely evil that it doesn't tell you that it failed to sample, because that means there's like, you should have gotten 2,000 samples, you get 100, and you think this is the profile, and you look for hot code in those 100 samples, and you're looking at something completely bogus. Okay, and something else that's not available here is code from the native threads. Why is that important? We'll look at an example just now. Now, to contrast this, we have Honest Profiler. Honest Profiler at least tells you when it fails. So if a sample is missed, it'll include an error code as its own method frame, and you will be able to see that you've missed something. It still can't see the stubs, it can't see array copies, array fills, and so on, but you'll see the errors. You'll know that you're missing something. Might drive you to look somewhere else, okay? And native code, still missing. Native code will show up as errors, which is good, because at least you know you're missing something. It's the whole known unknowns versus unknowns, okay? Here, you know you don't know something, and with Java Mission Control, you don't know that you don't know it. Finally, on this list, we have Async Profiler. Async Profiler uses a combination of an internal stack walking mechanism of the JVM and perf profiling to give you a view on native stacks and on Java stacks. It reports failed samples and minimizes them, so you get very few failed samples. It shows native, it shows user code, it shows kernel code, which is great. Currently, it doesn't give you line of code precision. It doesn't give you breakdown by thread ID either, but that's happening in the next week or so, I think. So it's probably a better tool to be using. To demonstrate the difference, I don't know where the browser went. Hello. Turned it up on this screen. There we are. Right. So now I'm the only one who can't see what's happening. All right. And it started from the end. Okay. I can only see it here. Right. This is the profile. This is a flame graph. Anybody used flame graphs? Knows what a flame graph is? No. Okay. Most of you don't, which is natural. You should have a look at it. It's a way of representing profiles. The width of a frame tells us how many samples are in it. So this is where all the time is spent, because this is the top frame, and it's the widest one. So in this benchmark, using reflection to get elements from an array is what's taking the most time. Now, using reflection to get elements from an array is a bad idea. But should it be taking all of that time? Isn't there anything else we can do to improve things? If we look at the same profile with JFR, we're getting this. All of a sudden, using reflection to get elements from the array here is not so bad. We get a much nicer, more detailed view on what's happening, but is that the full picture? And this benchmark is a serialization benchmark where we have some bit of JSON being serialized by a library, okay? we should expect to see a lot of GC because we're creating strings. We should expect to see a lot of memory copies because generating strings involves copying chars into the strings. We're not seeing either because there's no way for JFR to see those things. If we look at what async profiler is telling us, we see a completely different picture. In particular, where did my, oh, there's my pointer. We see GC, okay? And GC is how much? 50% of the samples are in GC. Now, it's not that currently there's no way for you to know that you're spending time in GC. I'm sure most of you are collecting GC logs in production to see what's happening. Correlating those GC logs with what's happening to your application is something that's quite difficult to do. Okay, and here we can see that if we spend time optimizing the Java code, we're actually wasting our time. Okay, the thing to optimize here is either the GC parameters. Maybe this application needs more heap, then it won't GC so much. It'll GC less often, more efficiently, it'll work faster. Maybe we need to be looking for redundant allocations and removing those. Looking for pure CPU efficiencies is not necessarily going to deliver the performance we want. Okay, so having the full picture is really very helpful in this case. That's okay. No, that's not okay. The joys of using I don't know what's happening. Let's kill the browser. Sorry about that. Yeah. Wonderful. No. There we go. Okay. So, if we're going to use JFR, you have to turn on debug non-safe points. You need to watch out for the sample count. And this is where understanding how samples work with JFR becomes quite handy. So, JFR doesn't sample on a timer, samples based on a trigger from the number of cycles you've spent. It's still a great improvement over JVisual VM. But when you're looking at a cycles tick profiler, which is what JFR is, honest profiler, async profiler, the number of samples don't reflect wall clock time. So if you've asked for 100 samples per second, the maximum number of samples you can get will depend on the number of cores. Okay, so the maximum number of samples you can get is the number of cores times the number of samples times the numbers of seconds. So if I have 8 cores on my machine, I can get 800 samples per second if I'm utilizing 100% of the CPU. That means that if you look at a profile you've collected with JFR over, say, 10 seconds, and it's got 100 samples, something is probably fishy, especially if the CPU utilization it reports is high. So you need to do a bit of math to match the utilization and the number of samples that you expect to see. This can become quite useful if you know what you're looking for. Okay, so we've looked at the traditional kind of Java profilers. We can go a level deeper and we can look at instruction profiling. Instruction profiling is something people do in native applications, and it comes from a realization that code is not something that actually happens to the JVM. Okay, there's no code, there's no line of code, because by the time the JVM sees your code, it's been compiled into bytecode. Okay, so we have bytecode. But if your bytecode is executed frequently enough, it'll get compiled into native code. So there's no bytecode at that point, there's no bytecode index. All we have are instructions that the CPU executes. And to do that, to look at samples of what's happening on the instruction level, we sample the program counter. If you've done a computer architecture course as part of your degree, this might sound familiar. The program counter, or the instruction pointer, points at the next instruction to be executed. So you fire up a signal, and you get back in your signal handler, what is the current program counter? Where in my application am I? What's the next instruction that I'm going to execute? It looks something like this, except the children being pushed into the meat grinder. The observation to be had here is that the program counter points at one instruction, but CPUs are not a single stage of just execute the next instruction. We have a pipeline of execution, and in that pipeline there are several stages, okay? First we fetch an instruction, then we decode the instruction, then we execute it, which is the execute in our mind that the CPU actually does, and then we retire it. From here, looking at the next instruction is potentially problematic. It's not actually the instruction that's getting executed, and that can lead to some misunderstandings. So, we have the program counter, it's the next instruction. How do we sample it? You don't really need to know this unless you're going to write a profiler, but the basic mechanics are you install a signal handler, you fire up a signal. The signal is usually based on the number of ticks, the number of cycles that's been spent, and then your handler is invoked. You get a view on what is the program counter, and then you can match the program counter with the assembly that is being executed. Now, most Java developers, me included, don't like looking at assembly because correlating assembly back to your code can be a pain in the ass. But if you are going to look at assembly and you're going to look at the print assembly that the JVM dumps out, you'll notice this on the left-hand side, way over there. There's some helpful comments, and the comments tell you where the assembly came from. So we're trying to correlate back and forth between the assembly and the lines of code. Now, the data fed into this profiler and the data that fed into this profile, it's the same data, okay? So maybe if we looked here, we wouldn't have to look at the assembly. But even in this case, if we're going to zoom in on where the cost is in the assembly, we can see something quite strange happening. This instruction here, this move instruction, is a move instruction between two different registers. Who knows how much should a move between two registers be? Moving data between two registers costs... Sorry? No. Costs nothing at all. It costs... nothing costs nothing, but moving between two registers should never be a bottleneck for your application. But the instruction before it is a division, and a division is massively expensive. This demonstrates a problem with this methodology, because the next instruction to be executed is a good indication of where the hot instructions are, only if all instructions are the same cost. Okay, if that's not the case, then the division instruction is always going to make the next instruction look bad. Okay, and there's a few of those instructions that happen, but you know, this is as good as it gets. So you know, we get a precision on the instruction level, and we get accuracy that is sort of cycle-ish. Okay, I don't know, ish doesn't sound that great. We have this observation on the mailing lists. I like this conversation because it's between two experts, and it demonstrates how much confusion there is in the field of profiling. Effectively, Instruction profiling is, because of the precision it offers, people have a false kind of feeling that it's really very, very accurate. It's accurate, but it's not, flawless. So we have some issues here. I'll just go through them quickly. There's non-uniform instruction cost, which I touched on right now. CPUs, even when we look at the pipeline as different stages, there's actually the pipeline, each stage happens in parallel to the other stages, so the pipeline is quite deep, and you have superscalar CPUs. That means the execute stage and the other stages have more than one thing happening at once. Okay, so it's not one instruction stuck inside the CPU that is hiding the cost. It's potentially 5 instructions that are happening in parallel. On top of that, we have out-of-order execution, and we have speculative execution, which means I can make progress and cost you cycles, and then turns out I was wrong, and I have to go back to the branch which I speculated past. And finally, there's a phenomenon called skid, which means I ask the CPU what's the next instruction, and it gets back to me quite late in the game, and I've potentially missed hundreds of instructions. It sounds really terrible, but the end result is something that can be summarized as this. When you're looking at the assembly, the blamed instruction is shortly after where the big problem is. It's not a huge problem when you're looking at assembly. On top of that, there's some progress in this field with Intel offering precise event-based samplings, which are available for instructions, for branches, and for cache events. Typically, your profiler is not using these events. It's using the cycles event that is not precise. But it's good to know that you can profile on other events which are more precise. So, is it completely broken? Not really. It just has slightly limited accuracy. It works well enough when you're working with an assembly-level profiler. The problem is nobody wants to look at assembly, right? It would make us as sad as poor Gollum at the corner there. So we want to go back to our lines of code. And this is tracing back what our profilers do. How does Java Mission Control know which line of code the instructions match up with? So the process works like this. You go from the instruction, the program counter, to the bytecode index. Okay, we try to do this mapping. Where do instructions come from? That's the question. I have an instruction, which bytecode generated this instruction? How does this mapping work? And it turns out it works in many different ways. Okay, sometimes it's a single bytecode to a single instruction. Sometimes it's a single bytecode to many instructions. And that sort of makes sense in our minds because we think that we're in a higher level language, and therefore one of our super expensive bytecodes will be many tiny, tiny instructions. As long as these mappings work, we can live with that because there's a definite bytecode we can blame, okay? Sometimes we have many bytecodes generating a single instruction, or many bytecodes generating a few instructions. This happens when the compiler cleverly detects that we're doing the same thing again and again and again, and it can just do it once. Now, which one of the bytecodes should it blame? Right? Should it be the first one? Because if we remove the first one, it's still going to happen for the second and the third time, and then the blame will just shift there. There's no way for profilers to describe cost that comes from several places. The information isn't there. The tools don't have that kind of representation. So this happens. And the last case here is a curious one. Sometimes no bytecodes can be blamed for the instructions. And that's particularly true for runtime-related generated instructions. For example, we talked about Safepoint pull. Safepoint pull is not something that you ask for in your code. It doesn't come from bytecode. There's other such events that you'll see. Sometimes it's implicit null checks or implicit class instance of, that you didn't ask for, but still there's instructions for them. Who do we blame for the instructions that came out of nowhere? We just pick the closest one. So just like when we had the Safepoint pull at the end of a loop, and we didn't know who to blame, so we just picked the next line after that. Similarly, this is what happens here, and this is, again, why you need the extra debug info, otherwise the distance between points I can blame will be very, very large. Okay, so we've blamed a bytecode index. Now we need to find the line of code the bytecode index came from. The problem is, again, not every bytecode has a line of code. Because you might be generating bytecodes via some AOP framework or some agent, or maybe just the JVM mutated your code into something that is not a one-to-one conversion. Okay? Again, we just find the closest. So there's no magic here. We have a mapping that is sort of fuzzy between the instructions and the lines of code. It's as good as it gets, and as the poster claims, 60% of the time it works every time. We need to look for other suspects nearby. So if one line of code is getting blamed and we think that doesn't make sense, we need to look for other lines of code that are sort of in the same vicinity. The problem is that nearby doesn't really mean what we think it means. Okay? You think nearby, I'll just look at the previous line, right? We skidded a little bit. It looked for the nearest thing to blame, so maybe it's the previous line. Because in our minds, lines of code come in an order. We write them, and things happen in order. But the compiler is free to remix all our lines of code as much as it wants and generate a new program that looks like it does the same thing. So we end up with something like this. Okay, line 1 to be executed is lines 10, 5, and 6 put together, rehashed to make something happen. So the conclusion here is that line of code in a method just generally sort of works. You can look for obvious wins within the same method. Use common sense. Don't just blindly follow the, oh, it says it's this line, so it has to be this line. Look at nearby lines, maybe look at the assembly. And looking at the assembly should be the last resort, but sometimes it can come in handy. Okay, if we can't find the right line, can we find the right method? Can we at least find hot methods in our application? And that would work something like this. We'll get a program counter, we'll map that to a method, that should be easy, okay? We'll find slow methods, we'll optimize, we'll win. Now, if that works, shouldn't Safepoint pooling work? Right, we said on method exit, there's a Safepoint pool. We should be able to find slow method just with Safepoint bias. And it should be fine, but really it isn't. Because I remind you that you'll end up blaming the caller, not the method, at least on Oracle. So the return line of code is blamed. You still need to look at the line of code. And now comes the real problem. This only works if the method is really there. But methods disappear. They disappear through a process called inlining. Who knows what inlining is? Awesome. Everybody knows. No, just about 40% of you know what inlining is. Great. Inlining is a really simple optimization. You take a method call and you just pull that method in and you inline that method into the caller. So instead of the caller having to jump through hoops to go to that method, it just executes the code of that method locally. And it's a great optimization. But it removes the Safepoint pull when it happens. When I inline the method, the end of my method is still way over there, and I don't take the Safepoint pull and keep it. And this doesn't sound like it's such a bad thing, and it's not a bad thing, but the result is that with JVisual VM, for instance, you can't see hash map get. So certain things just suddenly disappear completely. I've had conversations with people saying, I don't know why people look at data structures. I can never see data structure issues in my profile. The reason you can't see them is because all the Safepoint polls have been taken away and you're looking at a crap profiler. Okay, so we start with something that looks like this, okay, and then combining two effects together, we have inlining and reordering, okay. So method 7, that was way over there, is now the first thing to happen. All of these calls through read person, new person, 1, they've shifted around, some methods were eliminated. The imprecision that we had looking at lines of code has expanded in scope to looking at methods. Only now it's a lot more confusing. So the combined effect here is that on the instruction level profiling, maybe you missed 4 instructions, but one instruction was in method A somewhere deep inside your call tree, and the actual instruction you need to worry about is somewhere completely different in the code base, which can be quite misleading. This combination of tools will give you inlining data. We'll have a look just now. But the inlining scope is massive. Okay, the JVM routinely inlines 9 method deep. The methods that are generated are very big. It's a good thing for your performance. It's a confusing thing for your profiling. Okay, this is a flame graph. Again, most of you are not familiar with flame graphs, but the height here is one method calls another method calls another method. What we see here is that this method, which is green, it's a real method. It called string going to right, it called this. All of these are in here. So I can very easily slip from one method to the next method and get a very confusing result. So having this information can be valuable. There are tools that can give you fairly intuitive views into it. Again, method granularity kind of works. It works very well for real methods, but for virtual methods, which are the methods we just inlined, not so much. Maybe looking at the assembly is a good idea, especially if you are looking at a confusing problem. Not all the time. Don't start from the assembly. Okay. The next problem is, as if this wasn't enough, is that methods in a JIT compiled runtime are not a fixed thing. Okay. So the first problem starts for profilers. Most profilers assume that methods are fixed. They exist before you start your program. So they rely on static debug information. It doesn't exist for JIT environments. That's true for many environments, so there's already solutions for that. You just need mapping. So if you're trying to use perf, you will need to create some mapping information for it. That's great. That doesn't solve this problem, compilation over time. And as far as I know, no profiler at the moment offers you insight into this. But if I look at a method sort of life cycle, I have the first version, which is executed in the interpreter. Then I have, typically in current times, we have tiered compilation. So the client compiler will compile your method into another version. Then the server compiler, C2, will have a third version. And then potentially your method will de-optimize and re-optimize and will get a third and the fourth version. All of these are different methods. They're not the same method. They behave very differently, and if you mix them all together in your profile, you can have a very, very confusing time finding what is slow and what is fast. Furthermore, we have different versions of the same method when we start thinking about inlining. If I inline a method, I specialize it for the core site. In most profilers, there's no distinction between the inline versions and the full versions. Okay, so if we have this, method A calls method B as a combination that's equal to X, method C calls method B, we get Y, X isn't Y, and that relationship can be quite confusing when you're trying to make sense of the profile. Finally, we have utilization-related confusions in profile. Most of us work in multi-threaded environments, and your application has lots of threads executing different bits of your code base. So when we're comparing utilization in a profile, and we see method A getting 20%, method B getting 80%, we would tend to optimize method B, that is getting 80% of the blame here. The problem is that method B might not be the problem. Now, this is not the right screen. Okay. Okay, sorry. Hey. Great. And now I can see it, but you can. Right. If we look at this profile, the observation to be made here is that this part of the profile is wider than this one. And without going into details about what this application is trying to do, if this was all the data you had, deciding to focus on that side of the profile is the right thing to do, because that's where most of the cost is. But if we break down the profile by thread, we can see that the one half of the profile here is spread across many threads, and this one, that was the smaller part, is only executed by one thread. Now, I don't expect anyone to make sense of two profiles just by looking at them for 3 seconds. But this situation where you have one thread executing a particular piece of code, not letting other threads continue to do work, is very common in SADA-type architectures, which means you see it in practice quite a bit. If you are using something like Netty, and in your Netty thread you're consuming messages, decoding them, and then passing on the work to some worker pool, the worker pool would have many threads. The decoding thread might be running at 100% CPU. And even though the overall application is not overloaded, that one thread has become a saturated resource in your profile. So your application will not scale until you fix what, at the first glance, looks like the smaller problem. Okay, so comparing method utilization can be misleading if you're running in a multi-threaded environment, which we all are, which means you need to record the expected max samples. You need to have it in mind when you're looking at the number of samples. And then you need to record the thread ID so that you can have thread-by-thread breakdown of your profile and try and make sense of whether or not one of the threads is saturated. This is, again, not easily visible from a lot of profiling tools. So you can look at Oracle Studio. It does a very good job of visualizing thread execution and the samples per thread. I have 25 seconds. I will offer you as much comfort as I can after this in 25 seconds. So I was just sent this slide, this picture this week after being overtly negative to someone. And this is about Genghis Khan as a child. And what do we always say? I'm Genghis Khan, not Genghis Kant. So you can analyze profiles. You should be using a profiler. They give you lots of good data. You just need to be aware that they are not perfect. And contrasting the input from different profilers from different point of view and using a bit of common sense can really help you find the real problems in your application. That's it. Thank you very much. And we have 0 seconds for questions, but feel free.